Okay. Well, thank you everybody for showing up. Welcome to the February 11th edition of our working group and our two mini talks. I'd like to remind people that this meeting is live streamed and recorded and will be made available for public use after the meeting is over. As usual, introduce myself, James Glazier, Indiana University, Reinhardt Böttcher in Florida, although sitting in Connecticut today, and our team, Jim Sluka and Bruce Shapiro. Everyone hears from quite a bit. Remind you that we have a Slack channel, which you're free to use. If you need information on how to get to it or use it, please contact us. We also have the IMAG MSM wiki page that always needs love, so your contributions to that would be much appreciated. Again, if you need access, let us know. I was asked by a group at NSF to say that there is an NSF symposium on predictive intelligence for pandemic prevention. While much of this is focused on epidemiological modeling, it does have an in-host component to it. I would encourage people to check out the website for that. They're having a meeting, open meeting on February 22nd and 23rd, and they would love to have participation from our working group members. So I would encourage people to check that out and see if it's of interest to you. We have a number of very good upcoming mini-symposia, mini presentations scheduled. February 18th, we have Tomas Helikar, who does extremely interesting modeling of gene, especially gene regulatory networks, and also has done a lot of interesting work on outreach. We heard a little bit about some of his work a few weeks ago in the presentation from the joint French Luxembourgese presentation. You have Marie Ferguson, and then the following week we'll have Rita de Almeida from Brazil talking about analytic methods for trying to quantify gene expression in the context of SARS-CoV-1 and CoV-2, and Jim Fetter talking about modeling viral replication dynamics. As usual, we would love to have suggestions for speakers and volunteers for speakers as well. So with that, I don't want to take more time away from our speakers. Do we have Ruchira on the call?
Yes.
Okay, I will turn over the screen share to you. And if you can, as usual, I'll remind people that please try to keep things to 15 minutes so that we have time for some questions.
All right, now I'm on mute, hopefully. Everyone can see? Great. All right, so this is an invitation to approximate Bayesian computation for complex stochastic simulations. And since there's a very varied backgrounds among the people in this group, some of what I say will be familiar to many of you, but I hope that this is enough to get you an idea of what is the idea behind approximate Bayesian computation and to get you interested enough to look into it for your own simulations. So this being the modeling group, many of us are doing simulations. So the general scenario is we start with a specific model. We might be able to do model selection, so we could start with multiple different models, but for now I'll just talk about start with one specific model, and we fix a vector of parameters, theta, and we perform a simulation run. We let the model variables interact with each other. There might be evolution over time or over space of the state of the variables, and then we analyze the outcome variables of interest. So that might be a vector of variables x, and we might have different purposes in running this simulation. We might want to evaluate the mechanistic explanation. Our model might be embodying a mechanistic explanation of a phenomenon, or we might be wanting to make predictions. So the final outcome variables may be the things that we are trying to predict. So that may be the useful question that we're trying to answer with these simulation. So now, with stochastic simulation, we're introducing that there's some uncertainty in our model. So this could be because there are uncertain initial conditions. This could be because there's measurement error of the state variables, or the variables that are the independent variables in our model, or the observations also. Then another level is that there could be uncertainty in the parameter values themselves, and this is actually the scenario that we're particularly going to be interested in for ABC. And there could be inherent randomness. Now, what do I mean by that? So, in general, quantum physics tells us that physical reality in general is inherently random. However, there's a large class of models that we find to be computationally tractable and cognitively appealing, and that are useful, that are deterministic. So determinism is an approximation. And so when we talked about simulation in the first slide, we could have been talking about a deterministic approximation. But in some cases, depending on the questions the particular questions that we're addressing with our model, it may be that for those three criteria, it's actually easier. It may be more tractable, or it may be simpler to just use a random model. It may not be random down to the level of quantum physics, which may not be applicable. But even the approximation itself, it may be easier to use a random approximation of reality rather than a deterministic approximation. So at that point, our simulation becomes stochastic. So we need to use random variables in our model, and then we need to perform many different simulation runs. So we're sampling a space of many different simulation paths according to the different draws of the random variables. And then we need to analyze a distribution of the outcome random variables x. So we might want to characterize the range. For instance, if we have a vector of variables, we might find that certain states of different variables never occur together. That would be one characterization of the range. So initially, like 20 or 30 years ago, in terms of simulation, one would just play with the simulations and find interesting things. However, in order to use this rigorously, we want to actually estimate statistical properties like the expectation and other moments of these random variables. So in order to explain what we're doing, I'll just give an example which is in a simpler scenario than we just described. So this is Monte Carlo integration. So we have one random variable, capital X, with a probability density function, f of x, and we're interested in the expectation of a function g of x. So to get that exact expectation, the expression is that we integrate the function with respect to the probability density function, and then we get the expectation of g of x. So this integral, as it is, may not be tractable analytically. So we can do this integration by simulating realizations. So we can have n different realizations of that same random variable, one single random variable x. And so we're generating random quantities from that distribution with the probability density function f of x. And then we can approximate the integral by saying that the expectation of g of x is approximately the mean of these g of xi's. And so in this expression, we didn't have anymore the probability density function. It appears implicitly because we drew these probabilities, these variables from that probability density function. We simulated that probability density function. That's the basic scenario, and of course we're doing this multidimensionally. So a way of, now what happened here? That's not what I wanted to do. Oh, yes. So a way of doing this is with rejection sampling. How do I get back? All right. Okay, I'll just leave it like this. Okay, so we want to simulate this probability density function f of x, and in general, this density function could be quite complicated. And so in terms of generating random variables, we may not be able to, we may not know intrinsically how to generate that probability density function directly. So this is where sampling comes in. And so the example that I'll give is of rejection sampling, which is going to be important for ABC. So this is an example where we know how to generate a random variable with a uniform distribution. So suppose that the probability density function that we want to simulate, f of x, has support on an interval, AB, and we know that, and this interval, the values, the range of this probability density function is no more than m, some maximum, the upper bound of that range. So then we can draw the random variable x from a uniform distribution that is bounded on that same variable, that same support, AB. And at the same time, we can draw another random variable y, which is in this support of f of x, so from 0 to m. And so then we can evaluate f of capital X, our random draw, and then check whether y is less than that random draw. Y is less than f of the random draw. So this will then only, if this is accepted, if this equality holds, then we will accept our random draw as one of the random draws in our total sample, and otherwise we're just going to reject it and try again. So then there's some, it's a theorem that can be proved that the accepted draws will be distributed according to that probability density function f of x that we wanted. So it's a kind of a technique for simulating any probability density function, given that we know how to simulate random draws from a uniform probability density function. So now we had, that was an explanation of the basic idea between Monte Carlo, and generally In Monte Carlo integration that we just described, we were dealing with statistically independent samples. Now, instead, we want to deal with stochastic processes, and a Markov chain is a kind of a stochastic process that has the Markov property. So future states are independent of past states given present states. So it has a so it's a conditional independence, not the full statistical independence. We have a memory of one. So if we have discrete times, then we just need to know the previous state in order to get to the next state. So for a Markov chain, we have an initial distribution, pi naught, and we have a transition matrix, P of x given y. Now this is a shorthand that given the present state y, what is the probability that the next state is x? So again, this is future states are given the present state, and we only need the present state. We don't need any past states. If the Markov chain is reversible, which means that, so you can think of this is transition from y to x, and then there's also transitions from x to y. It's reversible, so we can get between any of these two states symmetrically. This is the equation. Then this Markov chain has a stationary distribution pi. And what we want is to sample from the stationary distribution. So in Markov chain Monte Carlo, we could have multiple cold starts. So those are the initial distributions, because depending on our sampling, it may be that certain initial points may not necessarily get to the full stationary distribution. Some areas of the state space may be inaccessible. So we have multiple cold starts. Then we execute this Markov chain, which is a random walk according to this stochastic process. So this is a burn-in, and then we sample from the stationary distribution. And one key issue is the mixing time. So the mixing time means that we have run this Markov chain long enough to get to the stationary distribution. And so that we will see that it has converged, and that the distribution that we're seeing is the same over subsequent runs. Then we'll realize that it has converged. Now, in general, so in approximate Bayesian computation, we have the word Bayesian. So this is from the Bayesian scenario. I had mentioned that one reason why we're doing stochastic simulations is that we may be uncertain about the parameter values themselves. So we can make inferences about the parameter values. Is that something in the chat? All right. Yes. Yeah, I have just a couple slides to go. So we can make inferences about the parameter values by starting from data. So we're doing the situation that I had described. We were going forward, simulating from, given the parameter values, then what are the outcomes. So the distribution gave us the joint distribution of the outcome variables and the parameter vectors. So then we could factorize this distribution in terms of a probability of parameters and a probability of the outcomes given the parameters. And so then with this factorization, this factor is the prior probability of the parameters, and this factor is the likelihood of the outcomes given those parameters. And this is what we find by doing many, many simulation runs in this Monte Carlo simulation. So we can invert this using Bayes' rule, and then we can find the posterior distribution, the probability of the parameters given the outcomes. So we may have data where we've observed the outcomes, and then we want to know what parameters can we expect from that data, so that we can perhaps use those same parameters to analyze new data. Now, a problem with this general idea is that computing the likelihood is often intractable. So in my talk title, I talked about complex stochastic simulations. Actually, any simulation where the likelihood is intractable, we could call complex. So approximate Bayesian computation is a likelihood-free method where we don't have to compute the likelihood in order to infer the parameters. So there's a very nice summary of the idea from the Handbook of Approximate Bayesian Computation that came out in 2018. Numerical evaluation of the likelihood function is replaced with an assessment of how likely it is the model could have produced the observed data based on simulating pseudodata from the model and comparing it to the observed data. So I'll just very, very briefly say the basic steps of approximate Bayesian computation. So we have a sampling density G of the parameters. So that's from the prior. And we generate a set of a parameter vector, theta I. And then we generate a simulation run. So from this generative model, we have y is simulated according to the probability of y given those parameters. So this step, it can be our complex simulation. So it's written in one line here, but it can be, an arbitrarily complex computer code, and there are methods for dealing with that. And then we compute a summary statistic, S, which is a function of y. And then we accept this parameter vector with a probability that's proportional to the distance of S from the observed summary statistic. So this is the key thing, the summary statistic. So we don't require that our simulation has to exactly give the outcome that we observed, the data that we observed. So that would be strict rejection sampling, that unless it gives exactly the summary statistic that is observed, we would reject it. And that would take, in practice, that would take forever. We would not get to convergence, because very few of our simulation runs would actually have exactly those values. However, now to be technically correct, we would have sufficient statistics. We would have statistics that are sufficient to say that it is from the actual likelihood. Even those may be too much. So the summary statistic is a computable, tractable set of statistics that we can measure from our data, and that it's balancing that it's tractable to get something close to that. At the same time, we're having enough samples that are accepted. So once we do this acceptance scheme, then the result is a distribution of parameter vectors. And then now that we have this distribution, then we can say that the data support various hypotheses, or that they're within a certain regime of the parameter vectors, and we can characterize the data. And so this has been, approximate Bayesian computation has already been applied in a variety of fields. It was first created for the field of population genetics. So with these, there were aggregate populations, and there were various characteristics of the populations. It's also been, so I've put a sampling here which are perhaps relevant to this group specifically. It's been applied in ecology, in host parasite systems, in infectious disease dynamics, in HIV contact tracing, and pathogen transmission. And this one I want to highlight, colorectal cancer development. This is where I first encountered it. So this I think is close to our physiological models. So there's actual complex complex models that include different crypts in the colorectal. They're the pre-tumor and tumorous crypts, cancerous crypts. And so this is a so in this is a case where we have this very complex stochastic simulation, and we're able to rigorously make inferences using ABC. So this is Sotorova and Tavare,
So
and then
I,
subsequent
I'm
colleagues.
I'm sorry, we're going to have to wrap up here.
Yes, this is in fact the last slide. So I can give further references, and I hope that people can ask me
Great.
questions about further references for this topic.
Great, thank you. I appreciate your patience with the very short format. So we're going to hold questions. Everyone has your contact information. We'll hold questions till the end of the meeting. And thank you, appreciate that. And again, I appreciate everyone's patience with the very short format that we have to put up with here. Okay, our next talk is Lucas Böttcher, using excess deaths and testing statistics to improve estimates of COVID-19 mortalities. Are you on? It looks like you said you're stuck. Where are you stuck?
Yeah, I traveled back to Europe some weeks ago, and yeah, now you know, like all borders are closed, right?
So, and I maybe will give you a warning if the time it gets short, because
yeah,
we have a hard deadline at 4, so we have to be.
I
don't want you to have I don't want you to have an axe fall on your talk.
Right. I try to be very brief. So yeah, thanks a lot for the possibility to present our work on excess deaths and testing statistics in the context of COVID-19. And I carried out this work with Tom Cho and Maria do Sonia from UCLA. And there are 2 parts. So in the first part, I want to show you some. It's more about data analysis, so using excess death statistics to improve or assess COVID-19 mortality measures. And in the second part, I want to briefly talk about using statistical testing models to correct for some of these testing errors and testing uncertainties in COVID-19 case numbers, or reported case and death numbers. So, and I think that most of you probably know about excess deaths and how to calculate these numbers, but I still want to give a period, let's say for the past 5 or 6 years or so, and then you can determine a historical mean and corresponding confidence intervals. As you can see here, the darker gray solid line and the lighter gray shaded areas, and then you overlay it with current mortality data, and you just calculate the difference between your current mortality and the historical mean. And sometimes to get the like excess deaths in a certain time interval. And then of course you can integrate over a certain time horizon and you get some cumulative numbers. And sometimes, so what you also find in some CDC reports or data like source files that they provide, sometimes they also calculate differences between the current mortality values and some upper or lower bounds of the confidence intervals. So you have to be a bit careful. Like even if people talk about excess death statistics, they sometimes use different definitions. And here is one example that shows the mortality or evolution of weekly deaths in New York City. And of course, we all know that COVID-19 hit New York City really hard in March and April last year. And here you see that like this pandemic led to an 8-fold increase in the weekly number of deaths in New York City, but then you had like this relatively rapid decay if you compare it with other jurisdictions. And so from March 10 to December 10, or sometimes you have some reporting delays, so so it's not exactly December 10 probably, because these numbers sometimes need up to 1 or 2 months to get reported. But you have approximately about 28,000 excess deaths in this time period. But the number of COVID-19 deaths, the officially reported number is about 20,000. So there's some difference there. But what you find is that for other jurisdictions or other countries, this difference can be even higher. For example, if you look at this example, Spain, and here we also have like these different age groups, and you see that in all age groups you have like a relatively large increase in the weekly number of deaths, also in March and April of last year. But here you also see the second wave, and if you calculate again the excess deaths in the specified time interval, you find something about 66,000. And it's again much higher than the reported COVID-19 deaths. And but there are also other examples. For example, Germany or some Scandinavian countries like Denmark had a relatively low number of excess deaths that is like in a similar range than the reported number of COVID-19 deaths. Although Germany, for example, they had a relatively high increase in the past 2 or 3 months. So there was some indicator of like a relatively high excess mortality in November and December, and also January 2021. So another possibility to illustrate these results is that you look at the like weekly and cumulative death rates or cumulative number of deaths, and you can illustrate it in such a way. And what you see is that there's always some difference between reported number of COVID deaths and the excess deaths, which are represented by dashed lines, and the other numbers by solid lines. But this difference is like really high, and I think maybe some of you have heard about these examples, Ecuador and Peru, and there are also other countries like Russia where you have a really high discrepancy between COVID deaths and excess deaths. And in Ecuador and Peru, the difference is like almost a factor of 3 or more. And and this is probably due to limited testing capacities in these countries. And that's why it could be also interesting or useful to, instead of using officially reported COVID-19 deaths or case numbers, instead of using these numbers, one could also use excess death statistics or numbers in certain mortality metrics. And you could, for example, think of the CFR or IFR or related metrics. And for the IFR, it would be quite helpful in certain jurisdictions to use the number of excess deaths instead of the number of reported COVID-19 deaths, because of this like really high discrepancy between these two numbers. And here I'm showing like it's yet another illustration of the same effect, but maybe a bit more bit simpler to see what's going on in these different countries and jurisdictions. So here I'm showing like the blue solid line shows that the number of excess deaths is 3 times the number of confirmed COVID-19 deaths. And the black solid line is just like a like an equivalence between these two numbers. And for the US, we fitted like this blue solid line is a fit across all different states. And here we found that there's basically a 13% increase in the number of access staffs, or like the number of access staffs is about 13% larger than the number of confirmed COVID-19 deaths. And in the left panel, again, you see like that for Ecuador and Peru and Russia and some other places, the number of excess deaths is almost 3 times larger than the number of confirmed COVID-19 deaths. And yeah, like if you're interested in how to apply these concepts and also error estimation and uncertainty quantification to different mortality metrics, you can also check out our article on the topic. We recently posted it on the archive and on the Met archive. But like in the last few minutes, I also briefly want to discuss like what types of testing errors and testing biases we need to account for in our like disease modeling, but also in the if we are using or assessing certain case numbers and mortality statistics, because like different tests are associated with different types of uncertainty, right? And it's quite important to account for these factors if we're using case numbers for like policy briefs, for example. So one should be quite careful because many of these testing related statistics has relatively large errors. And if we, for example, use rival testing like RT-PCR or rapid antigen tests that can detect current rival loads or current infections, we know that there are certain tests that have false negative rates between 10 and 30%. But if you're using throat swabs, for example, like these values can be like quite large, up to almost 70%. But the false positive rates are relatively low compared to the FNRs, about 5%. And for serological tests or antibody tests that can be used to detect previously infected individuals or recovered individuals and current infections, if there like was a certain delay, right, for the antibodies to develop, one can also use these tests. And they have, compared to rival testing, they have relatively low FNRs and false positive rates in a similar range. And these values, of course, can be translated into testing sensitivities or true positive rates. That means like these values give you the probability of identifying an infected individual as infected if you test him or her, and the specificity or the true negative rate gives you the probability that you identify like healthy individual as healthy and not infected if you're using one of these tests. Now, another factor, and that's probably even more important than the FPRs and FNRs, is testing bias. So there could be different testing biases. For example, like what is probably the most likely scenario is that you're biasing testing towards infected individuals because it's more likely that you're testing symptomatic people. And one possibility to describe such a testing bias is that you use such a bias testing function. So FB is the fraction of infected individuals accounting for testing bias, and F would be the true fraction of infected individuals in a certain jurisdiction. And here are different examples that show that there could be under-testing or over-testing of infected individuals, or completely unbiased testing. And these red discs would correspond to infected people, for example, and the green discs would correspond to healthy individuals. And like if you're combining all of these different ingredients, you find something like distribution or likelihood of observing a certain positive fraction of infected individuals that under certain assumptions, you can also write down some more general equations, but under certain assumptions, you can describe this likelihood function by a normal distribution. And you find that the mean, and that's also quite intuitive, is given by the fraction of infected individuals, but here still accounting for this bias B times the probability that you're identifying these individuals as positive. And then you also add the like falsely positive identified individuals, and then you get your mean. And if you rearrange these terms a bit, you can use this likelihood function to get a maximum likelihood estimate of the corrected proportion of infected individuals. And here you see that, again, like this is quite intuitive, right? You're taking your observed or apparent fraction of infected individuals, and you're accounting for these FPR and FNR rates, and also for testing bias. And this basically means that, just as an interpretation, that if you're given these daily test curves and the positive testing rates, you have to be careful if you go to relatively low percentages, because like at a certain point you're just seeing the testing errors. And it would be very interesting also for gauging these tests to maybe, you know, let it run for a longer time, even, that's just my interpretation, even if the pandemic is over, to see what kind of noise levels you get, but it's probably not something that is implementable. So just to summarize, these XSTAF statistics are quite useful for reinterpreting some mortality measures if the number of XSTAFs is sufficiently large. And you can account for certain measurement errors and uncertainties in testing statistics. And in general, like a recommendation would be that you should always try to include some uncertainty or error bars in your COVID-19 case numbers or death numbers. And if you're interested in some further literature, code, and data repositories, here's a list. And I think that these slides are also available online if you want to skim through or over again. Thanks.
Thank you very much. Time for a question or two for either speaker.
Can I start with Lucas?
Please.
So Lucas, it seems that you're looking at mortality and saying, okay, this number needs to be corrected somehow. Do you have, did you study data like US states or something like this? I saw a picture of New York, and which is, I see those numbers myself, but did you study the other states and can say something about it?
Yeah, so I mean, one thing that we studied, or like one plot that I can show right now, is this one, like excess deaths versus confirmed deaths for all US states. And you see that the number of excess deaths is always larger than the number of confirmed deaths for, or not always, but for most states in the US, it's larger. And there are some other plots that we included in the paper, mortality metrics, because you were asking for probably CFRs and IFRs. And we included like these numbers in like this paper that I'm showing here. You see all these distributions there. Maybe this is something you could.
Yeah, I'm less interested in the contribution in distributions. I'm more actually interested in what a human thinks. So if I consider you as an expert and I give you all 51 states with the numbers, can you tell me whether things are overestimated, underestimated, approximate how much you think?
Yeah, yeah. I mean, I think in the US,
No, not now. I'm saying, can you, if I give you the spreadsheet, can you actually tell me after thinking about it as a human?
I think so. So if you have historical mortality data and you have like current mortality data, and you can also say something about other factors, for example, like something that some people always ask about is traffic accidents and things like that, you can get some relatively accurate estimates of the actual number of deaths compared to reported disease-induced deaths. So that's possible. Yeah.
Okay, great. Because I'll be following up with you. You'll get an email from me.
Okay. Thanks.
I need several experts like you.
Okay. Is there one other quick question? If not, I'll turn the meeting over to Reinhardt. And people are certainly welcome to talk to our speakers individually, offline. Everyone has contact information. Again, I appreciate people's patience with the very short format. Okay. Reinhardt, let me come back to.
All right, thank you, James. Thank you to our speakers. It's very interesting talks. What I think we could do is essentially two things. I want to mention briefly one topic we've been discussing in the steering group, and since pretty much all work happens in the subgroups, and the steering group is made up of the leads of the subgroups, I think it'd be good to let everybody know, assuming you all signed up for one or more subgroups. But after that, I think, James, this would be a good opportunity. We have a little bit of time left to finally get to this idea of competition, hackathon type things that was discussed very briefly, but we never had a chance to really get into that. What I want to mention that we've been talking about for the last two steering group meetings and quite spirited discussions is where this working group should be going. Should we actually be doing something? Should we actually be doing? Of course, we're doing something, but in terms of actually organizing and doing and trying to fund one or more research projects, and there's lots of different ideas, and that's being discussed. So if you're at all interested in this, please get in touch, certainly with either one of us or with the leads of whatever subgroups you're signed up in. I think it's a great opportunity to organize research projects around a larger theme that has been brought out, I think, very clearly by this group and the various discussions we've had. So this is an opportunity for us to move forward. Okay, so James, I think we can go ahead and talk about competitions, unless somebody has a comment. Okay, go ahead, James.
Well, right. I think that was, I mean, that was our agenda. I think we rarely have time to discuss ideas generically for this working group. And so we have a few minutes, I think, to do that now. Is there a sense in the room about whether a competition model might be useful? Is there a sense in the room about whether the idea of actually trying to deliver models might be useful? If you look at the NSF proposal, the one we shared, they are definitely focusing on trying to deliver actionable models. And so there's certainly some overlap. Again, this group seems to be more, it has been from the beginning focused more on in-host modeling. The NSF project seems to be a little more heavily focused on large-scale models, although going down to smaller scales. We definitely appreciate people's opinions on these issues.
So James, on the previous slide, you had a slide up from the dream challenge, and you know, that was quite interesting. I know a little bit about that, and I think it'd be a great opportunity to see if one could organize something similar or along those lines. It'd be good to see what ideas people have and what format it could take. So the way Dream worked, at least for some of these, you had, let's say there were a few that I participated in on network reconstruction techniques. So there was a data set and everybody could use their favorite technique to reconstruct a network from the data. And then there was, you know, whoever got closest was one of the winners.
What would be, you could ask the question, what would be potentially comparable challenges of that kind? I can think of some, but they're all a little more technical. Could you take mouse murine data on infection and humanize it? Could you connect in vitro data sets to use in vitro data sets to predict in vivo results? Could we actually predict the effect of modification of immune response in certain conditions? There are many generic questions like that. Trying to narrow them down to something very specific where there was a single data set and a single response is not so simple. And those are places where people with specific domain expertise would be essential. And I'm quite open to hearing suggestions about what might be appropriate.
So my opinion, I think, because I like the the processes that you talked about, James, but I think, you know, a competition with, I'm not sure a competition is necessarily the best context for that. Because I mean, the implication there is that there's a winner, and the implication then is that there is a standardized method of assessing the efficacy of whatever it is that you have set your goal to be. So for the, you know, just a limited set of examples that you gave, I think it is an open question as what the best way to actually accomplish the mapping that you're talking about should be done, right? And I think that if, for instance, and this is just my own opinion, a competition involves the most accurate fit, right, at the expense of robustness, I think that is actually going in the wrong direction. So I think that those challenges might be better represented as a solution space, right? And a call, as opposed to something that's a direct competition, because I think, and this is just again my opinion, one of the benefits of this particular group and the structure of this group has been the willingness to collaborate and integrate across different approaches, and as has been demonstrated by several of the kind of organizing slides. I think I'm thinking of Fred's in particular. You know, this is a multi-component challenge, and thinking in terms of, you know, integrative approaches and collaborative approaches and that sort of thing, just in my opinion, is going to be more constructive. It doesn't give the, I mean, the challenge is, and there was a separate thread that John started about this, is that there's this belief that you need to have an elevator pitch. There's a belief that you need to have some easily packaged solution, which unfortunately is true, but the fact of the matter is that this is a complex problem with a complex solution, and the idea that you can compress it into something that you can describe in 15 seconds is just, in my opinion, stupid. So, but that is unfortunately the world that we live in. So I think trying to reconcile, you know, the limitations of that particular approach with what is actually necessary to do meaningful work in this arena, I think that That is exactly the challenge that we've tried, that's been the topic of the discussion in the steering committee. And I think, it's something for the wider group to think about.
Well, so one way of squaring that circle would be to make the challenge be one of replication or validation. So actually make it into something where your challenge is to be maximally collaborative.
Actually, the challenge should be not against the models or against something robust. It should be against human capability. You put a human on one side, you put the models on the other side. Whether the models can outperform the human, because this is basically what we're trying to do. Even if the models are not good, if they are better than human on average, then they are better.
So these are not going to be easy questions to resolve. And it may be that a challenge or contest format isn't the most appropriate for this group. But if people have suggestions about contest or formats that would be appropriate, they would be received with great enthusiasm. I know, Jacob, you have good ideas on this. I think it was an idea that excited people quite a bit. But as Gary has pointed out, there's a lot of devil in the details in terms of making it something that's productive and that people want to participate in, and that doesn't interfere with the collaborative and cooperative nature of the group.
So it shouldn't be within the group as it is just like this, but I have some experience with challenges. It's kind of tricky and they don't end well on the long run. It's for various reasons. Usually the human element there is the one that's problematic. So this is why I'm saying, if you do a challenge, you need to do it between eventually towards the goal you want to do. And the goal of the models is actually replace human reasoning. So do the challenges against humans like chess. They made computer chess competitions for years where players played against the computer. And then 1 year there was Levy. Levy was one of the chess masters. He bet that in 10 years from now, he will bet against the computer and he will win against the computer. Actually, he won that bet. But a few years later, no one could anymore. Same thing has to be done here, but it has to be done in a nice way. I don't know what the nice way is.
Okay, I guess that those are good points. Who was somebody trying to say something? We're running out. We're more or less out of time. But if there's a last comment from someone, that would be welcome.
So one quick thought I had, more than seeing it as challenges. So this is Srini from UVA. So we've participated in multiple exercises with CDC and also coordinated with NIH Midas group. And instead of pitting teams against one another, building ensembles of these models, I think that would encourage more collaboration. And you can still have which model contributes most within the ensemble. And we have seen this work in forecasting and also in designing good interventions at the population scale. So maybe it's worth thinking about what the equivalent of that is at a sub-human kind of scale.
It's very nice. I'm already doing an ensemble and people are collaborating within this group. Whatever they're doing in the Midas group is minimal compared to what is going on. Talk to me offline.
We should definitely draw on your expertise in terms of how to frame and organize these, Srini. Thank you very much. I think that with that, we're out of time. Feel free to suggest ideas. I understand that there's not a lot of time for everybody to speak. And we appreciate your continued appearance at these meetings and patience. And again, suggestions for speakers and directions to go that would be useful would be most welcome. Thank you, everybody, for coming.